Yo, yo, yo! What's up, everybody? Welcome back. Today, we are writing a canny edge detector, kind of maybe. Maybe. The real answer here is that we are working on a barcode scanner because we're working on a meal tracker, and I want to like keep track of all the ingredients in my fridge, and I kind of figure as I put the ingredients in, I can kind of like scan them with my phone, beep, 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 right? And so like it would be nice to be able to just quickly match like things in my fridge to numbers, and a barcode's a pretty good approximation of that. So yesterday we kind of like started on this. We started like writing a barcode scanner, and like we were kind of like on track. But then we started looking a little bit more closely at some of the photos I took on my phone, and you might notice here that if you were to look at this part of the barcode and say, is this black or white? It's actually like not like a trivial answer from the perspective of code on a computer, right? I was kind of hoping that because barcodes are such so high contrast that like I could just kind of like look in the area of a pixel and be like, is that dark? But like something like this needs some more love than that. So what I'm thinking is edge detection seems like probably a good first step, right? What am I looking at when I look at this strip here is kind of like, I am like, if you squint and like zoom out a little bit, when you zoom all the way in, it's actually kind of like harder to draw the line. But if you zoom out, you kind of squint, you make it a little blurry, you can see like a shape here, right? Like you can see a line. And so presumably we can like draw a box around that line, and then once you have the box you can kind of be like, okay, the stuff in the box is mostly darker than the stuff around the box on the outside, probably something like that. And then hopefully that gives us some like clean signal for dark and light. I haven't really thought it all the way through, because I figure my understanding of the problem will change as we start like implementing stuff. But anyways, it seems like a good first step. And if we were to try to like draw draw edges here, the first thing that we might do is we might just kind of like iterate downwards, right? We might go like blump, 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 and we might say like, hey, if the pixel below is like significantly different than the pixel above, that's an edge, right? And that's basically what, like, if you look at like edge detection, you're gonna see the words probably like Sobel and canny, I think, are like canny is here, one that I ran across, and then Sobel is another one here. These I've like heard of in the past. And so like this like simple idea of let me just like look down and see if like there's a big difference in the pixel above and below. That's like essentially what the Sobel operator is. Sobel, I don't know, whatever. Right? You see like they're running like a kernel on this is an image kernel. Image kernel hand wavy is like if you have like an image and you're looking at like this pixel here and you're trying to like apply some transform to it. An image kernel is basically like, I'll put a box around this thing and look at like the surrounding area of this pixel and like multiply it by the numbers in the box, right? So here, what they're basically saying is numbers to the left of me, above and below and directly to the side, like those are negative. Things to the right of me are positive. And then like you're basically just like multiplying the difference, right? So if you have like constant black here, you'll get like -1 on the left, or make constant color, you'll get like -1 times color on the left, +1 times color on the right, and those two things like cancel out, right? But if there's like a big difference, then this will kind of like become a large magnitude, and you'll might see like a line, right? Now, just looking at this, I assume that that won't be good enough, right? That is like so fucking noisy that there's not like a clean line as it is in the picture, right? So I think that when I was reading kind of like the steps of the canny detector, it all seemed like stuff that I would do if I were to sit down and think about the problem a lot, right? So they're kind of just like, yo, blur it a little bit, like huck a blur on that fucker, and then use the Sobel thing that we had before to like generate a gradient, and then like kind of like squish gradients down if you have like kind of like here, if you were to draw the gradient as you go top to bottom, uh, yeah, let's do this. Here, if you were like to draw the gradient top to bottom, it would kind of look like Can we pick like a red here? It would kind of look like no gradient, some gradient, right? It was kind of like some gradient, and then like maybe like a little bit more gradient, and then like a little bit less gradient and less gradient, like whatever, right? I don't really know what it looks like, but like they're kind of saying like, hey, this thing has like gradient in all of this area, and like we might want to like collapse that thing to find like, if you have like soft, hard, soft, just like collapse that to the hard gradient in the center, basically, is essentially what they're saying here. And then they're like, just fucking like threshold some stuff and like try to connect lines, essentially, is like what they're doing. And all of those things kind of make sense. So I'm thinking plan for today is to just try to like take some ideas from this thing, see if we can like get some cool edge detection working, see how like each step of this thing, you know, improves the edge detection, and then hopefully we'll like rip through all of that and we can like try to process our barcode into something a little bit more reasonable. That's kind of the plan for the day. Yeah, I want to start with like the Sobel operator. That seems like really straightforward. It's never gonna be 100% accurate though. I agree. I understood. But maybe it'll be good enough. We'll see. We also have like a lot of space on a barcode to like work with, and we have like time because we'll be taking video. So there's lots of stuff to work with there. But we'll see. We'll see. Okay. But to start, let's just do a simple Sobel operator. So we yesterday, or in happy hour today, kind of like generalized the idea of an image kernel. So looking at this thing, we should just be able to like huck these numbers into a box and kind of see what they do. So let's kind of start there. I've also got some like sample images that aren't barcodes, that I just took while I was walking my dog this morning. I think something like this might be interesting to look at, right? There's like some very crisp edges here, and that way we can kind of like play with the thing on something like a little bit more complex and then dial it back to the simple case of the barcode later. That's what I'm thinking at least. So let's work with this guy. Let's work with this guy. So maybe it would be nice, actually, if our image in this guy that we're in our like little playground here, should just come from like standard input. Args 1. We'll just do this for now. Okay. So it should be that now I can just pass in whatever the fuck picture this was. This one. I like this one the best. So can I just like fucking slap a little paste here? No. Can I copy path? Was this one? Yeah. Can I copy path here? Yep. Okay. Now, this is going to fall over because all of this stuff is like barcode processing. So just if false that shit. Keep that for later. And okay, let's try running an image kernel on this thing. So, how do we do that? I guess we make like an output image. Which is probably, it sound like this thing looks signed to me. Right? It looks like you have like a gradient that is generated by this thing that could be positive or negative. So I think our output image is kind of signed. So let's do like some I16s or something. That seems kind of reasonable. And let's allocate some space for this thing. And actually, how like fucking high res is this? This is like really high res. We could downsample in code, and we will have to do that eventually. But for now, I'm just gonna downscale in GIMP first. I think that's easier. I think that's easier. So can we just do like image scale? Can we drop this to like, dude, like 1024? Yeah, we don't. We could go. Maybe we crop some and then downscale, because I do want to preserve like some of the blurriness on the original. So maybe we do like, what if we just like crop out this section or something? Crop, 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 crop. Okay, so now we are like 2K by 1K. Yeah, maybe that's fine. That's like, yeah. That seems reasonable enough for me for now. Okay. So we copy this guy's width and height. And we do something here. We create an image kernel. So this is going to be our horizontal gradient kernel is an image kernel. Oopsies. Probably i16s. Have you worked with threads in Zig? Yeah, a little bit. They don't come up that much, actually, surprisingly. Because I prefer using event loops when I can. Okay, so what does this thing look like? He's basically giving a little bit more weight to the current line. You could do this as like -1, -1, -1, and 1, 1, 1. But -1, 2, 1 is fine as well. So they're going -1, 0, 1. And then they're giving a little bit of more weight to the center line, which I think is reasonable. Makes sense. And can we just go like 4, 0 out? This needs to be tried. For this, for each horizontal pixel and each vertical pixel. Okay. We take the horizontal gradient kernel and apply it to the input image. Okay. At this X and Y, which I think are in the wrong unit. Which is fine. Not ideal, but passable for now. Have you seen the I.O. thing Andrew was talking about? Yeah, it seems pretty cool. Seems pretty sick. Isn't the point of a barcode that's effectively encoded into 1D? Yep. But you can use the 2D information to like try multiple times. And you can use the 2D information to process the barcode. Like, you have information from that, right? Like, if you were to limit yourself to one strip, you know, it would be harder to diagnose like the shape of this if you only had like one vertical slice of it, right? So like, yes, when you are scanning, the information is 1D, but like the presentation of that information is 2D for eyeballs, right? Or like however the fuck you want to call it. You know? Can we just do this? I think so. So this should give us something, and we need to like visualize this output somehow. So can we do write ppm? Let's make an output file of i16, and let's color like left direction as red and right direction as blue. I think makes sense. So let's say that we have this guy, and if val is less than 0, let's do something like we write red and then 0, 0. But this needs to be the absolute value. And then I think int cast here might be wrong. We might have to think about this a little bit. It might be out of bounds of a U8. But it'll crash if that's the case, and then we can fix it then. Then otherwise, we write it as the blue one. Okay. I did something wrong? What, though? Oh. Wrong type here. Okay. Okay, so we can, that felt like it took a long time. But we did get something. Where is our output? That was July 7th, 12:05. So that would be, or 14:05? 14:05. So, none of these? Hello? I think we didn't write it out. Wow. Why do you think like this? U16 here. Or I16, sorry. Okay. Okay, yes, that intcast is not happy. So, if we think about this, what is like the maximum value that could come out of this kernel? If the difference is large, it's like U8 times 248. Yeah. So can we shift this right by 8 or by 3 to divide by 8 again? Then I think it should work. I think. Wow. This is slow as fuck. I actually don't know. It would be interesting to see like what is taking so long. So can we do std debug print writing to file? And this is you know, calculating gradient. Whose fault is this? 2 Mississippi 3. Yeah, okay. So it's writing to file is taking a long time, and it's probably because we're not using like a buffered writer. Var buff writer is, you know, stood IO buffered writer around this guy, and then this buff writer, and then defer buff writer. Flush. Okay, let's try that. That should speed things up significantly, I think. So that we're not running like byte by byte. We're not calling a syscall for every single byte. Let's go, baby. We're so back. And let's take a look at whatever the fuck that made. Okay. So that's pretty interesting. We can kind of see. It might be interesting to overlay this on top of the original image. You know? Might be. Or maybe we just look at the original image. You can definitely like see the branches coming through here, right? If we look at the, oh no, the original is oh, hold on. I wanted to do this on the smaller thing. I forgot. I forgot. Okay. I can't see shit. It looks black. It is very dark. We could try to brighten that shit a little bit. We could try to brighten that shit. There, can you see that? I think that should be visible. We could maybe get even a little brighter without it going too bad. No, it doesn't like that. But we could clamp this. Okay. There we go. That's pretty bright. Right, so this is horizontal gradient. Horizontal gradient, right? So you can see here, like along a tree branch. Where's the original? Where is the original? Right, so like this here is like this thing here, right? So you can kind of see like horizontally we have some sort of like gradient-ish, right? Now, this is a lot, right? If we wanted to like outline maybe like these branches, it's I don't really know if this gives us what we want, right? So, like you can see here, for example, like you've got like a really fat edge here, right? That's over like very many pixels. If we wanted like a strong border, we'd have to do more, right? So I think that's where like the canny edge detection thing comes in, is we like start doing extra steps on top of this to get like crisp edges, I think, right? So let's kind of start working through it. Okay. So they say start with a little blurry. We could maybe try that part later. I'm interested more in gradient magnitude thresholding or lower bound cutoff suppression to get rid of spurious response to edge detection. So I think what they are saying here is find locations with the sharpest change of intensity value. The algorithm for each pixel in the gradient image is compare the edge strength of the current pixel with the edge strength of the pixel in the positive negative gradient directions. If the edge strength of the current pixel... Oh, this is actually something that I forgot. We have only done one direction. He wants us to actually he wants us to run the Sobel operator in both directions and attach a magnitude and a direction to each gradient, right? So you can imagine if you have like a really big up and really narrow like small sideways, that's essentially something that's like this way, right? So we can kind of store like basically like the Pythagoras of this shit, just like store it as magnitude and direction. That's what they're saying to do here. So let's do that. Let's try to yeah, I think that we can do this, and then we can visualize the magnitude of the edge, and maybe we color it according to the direction. I like that. Let's try that. So this now, what we have here is the horizontal gradient kernel. This output is now this output can still be the output. But it's going to be calculated slightly differently, right? So we're going to have the x gradient is the same thing, but we need a vertical kernel as well, which is basically just this thing like flipped mirrored, right? So you need to define your direction, but it probably doesn't really matter. But they did in the Wikipedia negative on top. So -1, -2, -1. This is going to be 0, 0, 0, and then this is flipped here on the downside. I prefer... I don't... I feel like I'm going to run into less problems if up is up. Right? So I think that this will make more sense to me, and so I should just kind of run it this way for now. Okay, so we have the x and the y gradient. I think we do have to apply this on every single pixel, okay? So can we then stash this shit? Our output now is not just like a single number. I think it's an I16 plus direction, right? So can we call this like a gradient that has a direction? Which is just like radians 0 to 2 pi, I think is reasonable here. Maybe negative pi to pi, not really sure. And magnitude is I16. Sure. So here, mag is x times x plus y times y square rooted. Okay. I wonder if this should be a float as well. Does this thing do like integer square rooting? Only for unsigned. Only for unsigned. So let's do float. Let's do floats. That's easier. I don't think it really matters anyways. Doesn't really matter for now. Maybe later it's like an optimization to do integer work when we can. But fuck it. Okay, so we have the magnitude. I guess what we should do is actually do float conversion here. I think that'll make our lives a little bit easier. And then what happens? Now we don't have to do... no, it is better to have these guys as I-16s here because then this multiplication doesn't hit floating point precision issues. Yeah. But we can do this. Const x grad f is an F32 float from int of x gradient. And we can do this like this. Now this becomes much easier because... no, this is the same. This is the same fucking problem. But... I guess we do like stud math a tan 2 of... I assume this is yx. Yeah, y grad f and x grad f. Okay, so this should be the angle. And then it's just like out at whatever the fuck we are. Y times out width plus x is equal to magnitude is equal mag and angle is angle. Seems reasonable so far. Is direction. And this is inner or data here. And why is he pissed? F16, I'm fucking off my rocker. Never fucking use F16s, that's crazy. Okay, right ppm gradient. So, what does this guy do? What does this guy do? Let's just write the magnitudes out for a minute. Mag is val magnitude. I guess we do something like where the fuck am I? Where the fuck am I? We do something like... Sorry, my dog is like a little bit antsy. I just want to make sure that she's not like freaking out. Mag over 2, probably because we were shifting light by 1 here. Then like clamp this thing to 0 to 255, and then like out is a U8 int from float of this shit, and then hopefully that kind of ends up with us in the right spot. Okay. We do have to call the new function, grad. Okay, he doesn't like that because integer overflow. So that means that these values need to be bigger, so having them come out as I32s should make that a little bit nicer, which also means that probably later we're going to be like uber clamped, but whatever. All right, so this is already interesting. This is already interesting, right? We're starting to see some real shit. You can tell here that there are some gradients like inside the branch that we might, want to blur out or maybe threshold away, right? So I guess this is kind of like, where is this? This is, I can't, centered-ish. Yeah, this is like here. Right, so like somehow out of this, we've managed to get some sort of squigglies in here, which isn't really ideal, probably. Right? So maybe it's time for us to apply that like little blur that they were talking about, right? Maybe they're right. Maybe they know what they're talking about. Maybe. So can we just like huck this guy in here? Blur. This is probably U16 is fine. Uh, 2, 4, 5, 4, 2. I assume this is mirrored on the bottom. 4, 9, 12, 9, 4. And then 5, 12, 15, 12, 5. We could probably calculate this, but I don't really give a fuck right now. Okay. So we start by... I guess we need to blur the whole image first. So blurry is image. We like copy this guy and we like rip the image. And the output of this thing in blurry is just probably like blur kernel apply on image XY. He needs int cast on here. Gross. Gross, but whatever. And then this needs to be divided by whatever the fucking number they said, 159. And then it should fit in the U8. So now, when we're working on these guys, we're working on the blurry image, not the original. Cool. And let's kind of see what that does. And we should probably say here, applying blur. All right. Applying blur, calculating gradient, running to file. And you can see that the, bullshit here is definitely decreased. Which is cool. Which is cool. Okay. My dog is like really antsy. I think she has to shit. And unfortunately, I can't just make her, I can't just let her shit inside. So I think I can kind of do a little 10-minute round trip. 10 minutes. So we will do that because unfortunately, there's nothing I can do. It's just gotta go that way sometimes. BRB dog shitting 10 minutes. How do we feel about that? Okay. Back at it. Where were we? We were trying to... Right, we had just visualized the magnitude of the gradient at each position, which seems pretty good so far. So far, that seems pretty good. It'd be cool if we could visualize the direction too. So I guess it's like we just do sine theta and cos theta, right? And like slap that into the picture, probably. Right? So here we say, where are we writing this thing? Where are we doing? It's like, x mult is, sine of the angle? No. Cosine of the angle. and this is sine of the angle. And then what would be great is like, can we visualize all 4 directions easily? We have 3 channels, so you can't just, we could just do the magnitude of this. I think that's the easiest thing to do. And then it's x mul times out here, y mul times out, and 0. So that should give us red and green. I guess here we can keep this thing as a float up until here, and then int cast it, or int from float here. I think that makes sense. Okay. Yeah, so you can see things that are heavily in the x direction are mostly red. Things that are mostly in the y direction are mostly green, and then it's yellow on the diagonal. So I would say this looks like a success in terms of gradient finding. Now, keep in mind, this looks a lot like edge detection, but it is not quite there yet, because these lines are thick with 2 C's, baby. And so probably what we want to do here is move on to the next step. Okay, so here I think what they're saying is, yo, look along the direction of the gradient. Sample a pixel, you know, up and to the right, down to the left, whatever. And if our edge strength is smaller than one of those guys, then we discard it. Now, what I don't really know is like, how far is it normal to look here? Do we like just look at the adjacent ones? Do we scan like, oh, here we go, 3x3 filter, small set of discrete directions, and then moves the 3x3 filter over them? Oh, that's interesting. Yeah, I see. So you just round it to the nearest 45 degrees, and then it's really easy to figure out where your check should be. Yeah, and you can just you only have to look between 0 and 180, right? So I think what they're saying here is you kind of categorize the direction as like one of these 4. 1, 2, 3, 4, right? And then depending on this one, you generate like boxes, right? So this one would look like, your kernel would look like, I assume, something like this, right? And then on this one, it would be like this and this. This one would be this and this, and this would be like this and this. Then you just run the kernel, I guess, is kind of what they're saying. And what are we actually trying to figure out? We're trying to suppress us if we are greater, if we are like the biggest of the 3. So maybe a kernel is not, it's not really what we want, because right now our kernel kind of automatically sums here. I don't really know if you can get like a max out of this thing easily. Oh, what we have. But I guess we could just add a function to our thing to do that. So this apply function is like actually kind of like sum. And then we could have a, you know, max. Even that is not really what we want. Let's just not use the kernel here. But I do like the idea of snapping to like 45-degree increments. That feels pretty good. So here we're doing suppression. Two P's probably, yeah. So here we iterate over the image again. And we say, hey, if what's the fucking direction of our gradient? Which maybe you could do. Yeah, you kind of need all of the gradients before you do this. So you do need this. Let's rename out here to gradient. Boom, 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 boom. And now I guess that means that we need a different type of output here. So what is this? This is now just, I guess this is still a gradient, but like suppressed. Okay. So we're looking at the gradient data here. And I guess it's like, you know, in gradient is this. We need to look at, the angle. So I guess we want like, maybe we have like an enum that's like direction, like gradient snapped grad-der. And it's like north, south, east, west. Can we call like, maybe we'd say like right, up, up, right, up, left. I think that's kind of what we want to do. We want to say like from angle. Okay. So what does this do? What does this do? It's like I'm thinking. Do we just like angle divide by 2 pi? So this will give us like normalized. Then we multiply this by 8 because there's 8 possible directions, right? Is that right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so we just snap to I guess one of these is duplicated though, right? Because this is both 0 and 1. So that means that we need to multiply this by 9. Yeah, so like map to 0, map angle to 0 to 9. Round. Then mod 8 to get maybe mod 4. And then here we just do it in the right order, and we can just do it in from int. Note 9, not 8, because right is double counted by, 0 and 2 pi. Okay. That seems right to me. To round, and then we do like, I don't know. Rounded is round to round, and then there's like int from float. I don't know. And then rounded %4. And can we do like enum from int? Okay. Can we right click test for this? Grid snap. So can we do snap grid-dir from angle of 0? This should be right. Obviously 180 this should also be right. 90 should be up. And 270 should also be up. These are wrong. These are supposed to be in units of pi. So pi 3 times pi over 2. Okay. He's mad about some other stuff here. Can we just like comment this out for a second so that the test can run? Rounded. Oh. How does like mod work with negative numbers here? Zig Lang reference. I guess we can just assert. Let's just this. I'm gonna assume that this is greater than or equal to 0, and if it's not, then we'll have to heal it. But now this works easier. Okay. Really? Okay, so he's mad. Pi did not return right. Which is surprising to me. So we have what? We have pi over 2. Pi over 2 over pi. So this is 1/2. 0.5 times 9 is 4.5. So this rounds up to 5. 5 mod 4. Yeah, this is wrong. This approach was not correct. 1, 2, 3, 4, 5, 6, 7, 8. Oh, because this is 0. Oopsies. Yeah, I'm just a dumbass. I'm just a dumbass. Good thing I wrote the test, so I wasn't confident. Okay. Still wrong? Okay, let's think about this. This is pi over 2 over pi. So this is 0.5 times 8 is 4, right? So this is 4 over 4 should be 0. So what the fuck is wrong here? Like, what is it complaining about? What the heck? What's up, how you been? Good, how are you? Fuck. Fuck! Oh. It's actually this one. I'm a dumbass. I'm a dumbass! I just was testing the wrong thing. There we go. Oopies! Oopies, oopies. Okay. So 4 should be upright. And times 1, 2, 3, 4, 5. Oopsies. Cool. And then up left is times 3 and times 7, probably. Okay. Okay. So now, I mean, we could test like some like ranges as well. But I'm not really too concerned. I think it's fine. I think it's fine. This will work. This will work. So we take the input gradient, we try to snap it to one of those directions. Okay. And we probably do something based off this. Right? So if it's up, we sample above and below. This is sample left and right. This is sample top left and bottom right. And this is sample top right and bottom left. Okay. So I think what we do is we just return the indexes here. So can we do like a... Yeah, let's do two coordinates. So this is like x minus 1 y, x plus 1 y. Okay. X is unsigned, so saturating sub. And then we'll clamp the top side later, I think. Okay. Yeah. Above and below, this is x stays the same. And then y... It doesn't really matter which order. I don't think. So this is top left. That's minus minus and plus plus. And then it's top right, which is x plus y minus, and x minus y plus. It has to be. Yeah. Yeah. I think that's right. I think that's right. Okay, so we have like this sample chords. And now we just say for sample chords, sample chord. I guess we kind of want like what we're picking we're checking like if the sample chord value is greater, right? So we need to like, first of all, sample. Can we do this? Here, let's do this. Mutable? Oh, it's fine. Sample chord is equal to the minimum of the height, the width minus 1. Yeah. And sample chord 0. 1 is height. Okay. Okay. Yep, this is looking good so far. Like this? Yep. Okay. Now, what do we do with this? We like... If we take like image, no, gradient at data at sample chord 1 times gradient width plus sample chord 0. Okay, yep. Compare. If compare magnitude. Does it have to be the same direction? Probably, right? Surely we need to be looking. We only care if it's going in the same direction. It seems like almost certainly. Yeah, same direction. Yeah. Okay. So we're close. We're close. We're close. We're close. We're close. So I guess it's like we start by setting the suppressed data at this to just the input value. Then if either of these are larger, yeah. If comparator is equal to, I would like to keep this guy around. So if this is equal to they're the same direction. And compare magnitude is greater than in magnitude. We replace our current location with nothing. Yeah, we just set the magnitude to 0. I think that makes sense. I think that seems reasonable. So we just say, and then we probably break, right? Because we don't care anymore. I'm like not against it. That like might work. I'm curious to see. He's mad. Angle is not always equal to 0, so we have to fix that. If while angle is less than 0, angle plus equals to math pi times 2. Fuck you. Fuck you. Fuck. Integer part of floating point out of bounds at 435. How is that possible? Is it like can we... Is it some, like, dumb shit? Like, it was actually, like, just a little bit under 0 or something? No, that should be fine. So this was, like, negative pi instead of pi to 2 pi. So, like, negative pi plus 2 pi should be, like, a round pi? Okay, what is 2 round? And this should new line, or else we're not going to be able to parse it. Negative 2? Negative 2. The fuck? Oh. We do have to have the number be bigger. Yeah. Thank you. Much better. Okay. I wonder what we got. Oh, did you guys see that shit? Did you guys see that shit? So now we should be seeing like really crisp lines. That actually is fucking sick, dude. Wait, look at that shit. Okay, well, let's go back. Can we write the... hold on. Out path. I think that it worked. Shockingly. I guess not that shockingly. But a little bit shockingly. Okay. Can we go back? Exeg open out 2 ppm. Right, so this is the gradient with, like, kind of just raw. Then, like, this is the gradient kind of after filtering. So where was this? This is kind of like up here, right? So kind of by this branch. Do you see how like these lines are like super fucking crisp now? Look at that shit. Right, so we've kind of just deleted anything that's like not like the inside most piece of the line, right? So like this was this here, and you see how like this is kind of like blurry, and this is kind of like nice and crispy. So that's pretty fucking sick. That's pretty cool. So I guess it worked. Okay. So we got through blur. We've got gradients. We got gradient magnitude thresholding. Hype, dude. Double threshold. Okay. So here, I think, if I remember correctly, some edge pixels are caused by noise and color variation, right? To account for these, it is essential to filter out edge pixels with a weak gradient value and preserve edge pixels with a high gradient value. So here we just say, you could just say, hey, discard anything under a certain value, right? But you can also say, hey, discard anything under this value, but also like mark anything below another value as like kind of like unsure, right? So they kind of do like something along the lines of like, if these are all of the magnitudes, you kind of have like, fuck these ones, get these guys out of here. These ones are like, maybe. And these ones are like, definitely fucking edges, right? And I think what they do is they then, to figure out if these ones are like actually edges or not, they check if they're connected to these edges, right? So they kind of just say like, for each pixel, I guess you probably have to do like a breadth first search or something, some sort of like actual walking of pixels, probably. Yeah. Blob analysis applied by looking at a weak edge pixel and its 8 connected neighborhood pixels, as long as there's one strong pixel involved in the blob. Oh, okay. So they're not walking the whole edge. They're just checking, they're saying like, hey, one of them is probably fucking close. Sure. How is this related to the barcode? We're going to use all of these strategies to turn this into something like solid, right? So like this you can like see with your eyeballs here that like you can kind of like parse it, but like when you get down into like the nitty gritty, it's like really not clear kind of like how thick this thing is without doing some sort of like image pre-processing. So I'm hoping that after we finish this, we run the canny thing on this and we get like really crisp, clean lines. That's what I'm hoping. Okay. Cool. So, yeah, I guess we just set some thresholds. Set some threshies. And do double threshing. I guess part of me wonders... yeah, fuck it. Okay. So, first of all, I guess it would be nice to get like a histogram of all possible values. I think that is not super trivial to generate, but maybe we could get the min and max pretty easily. I guess that's probably fair. I mean, can we like is the magnitude something that we should be able to figure out? It becomes way easier to reason about probably if here, when we calculate the initial gradients, we just clamp them into the range 0 to 1. Yeah, so here, we should probably find like the maximum value that this could put out, which is like 255 times 8, I think. Pretty sure? Because here, if you have 0, 0, 0, 255, 255, 255. Or maybe times 4. Because these guys can't be negative. So this is probably the maximum difference, except it's actually probably 256 times 4. So divide by 1024 is probably the right answer here. Then these guys can all be in the range 0 to 1, which makes calculation downstream probably easier. Because why? Because then you know the maximum magnitude will always be 1. It can't be higher than 1 if you do that. Yeah. Let's do that. So here it's magnitude divided by, I think it's like, okay, we do F32, float from it here, get the square, then we do mag divide equals mag divided by 1024 divided by 1024, because we have 1024 here. I think it's after the square root, actually. I think. So now, hold on. So we have like a circle here where we have like 1024, 1024. Then you have like, once you do a squared plus b squared square root, it's always going to be like on this arc. So this length will never exceed 1024. And then that means that here we can do mag divide equals 1024. You usually think about something how to do you usually think of how to do something in your head, or how do you know when to whip out the drawing tool? It's like, I mean, I just whip it out when I get confused, I guess, is the answer. But yeah, I think that my visualization in my head is like decently good. Like, I know that like everybody kind of thinks things differently. I think that I can like make like maybe like a 7 out of 10 strength picture in my head. Sound I can do really well, actually. Like, I can like probably get like a 10 out of 10 sound in my head, which is kind of crazy. Like, sometimes I like can like convince myself that people are like in my house. Like, I can't really tell the difference between like sounds I'm imagining and sounds that, not imagining, sounds that I'm like intentionally creating with my brain and sounds that I'm hearing with the real world. I can like easily blend those. But yeah, images, it's like maybe 7 out of 10. So the drawing tool is when I get stuck. When I need that 10 out of 10. All right. All right. So now probably something downstream broke here, I assume. I think it's actually just the writing of this stuff. Instead of clamping this, can we just do mag times 255 here? I think that brings us back to the correct range if it's always 0 to 1. Kind of see how that plays out. Does look like that's right, and if I refresh this, yeah, that's about right. That looks about right. How long have you been programming for? At least 10 years. Probably longer. Yeah, maybe on the order of like 15 years would be my guess, but I honestly don't remember when I started. Oh, probably longer. Maybe 20. I guess like my first exposure was like a summer camp that my dad ran for us when I was like 10. And I'm like at least 30. What year is it? Odd number year. So I'm probably like 32. Probably. So like that's like 22 years. But like obviously at young ages, it's like how much does it really count? Who fucking knows? You look 22. Okay, you don't have to lie. Okay, so I think this is like basically fine. Now we know. Now we know that this thing will always be between 0 and 1, so we can set thresholds, right? So can we just say like if suppressed we also want to do if in gradient magnitude is less than, you know, lower thresh, we just like nuke that shit. Then probably we add like a confidence here. Maybe we just set this here. Like, no, maybe, yes. And that means that here we can set the magnitude accordingly, right? So we can say confidence here is no. Else if in grad magnitude is less than higher thresh, confidence is equal to maybe. Else it's yes. So much indexing. I thought it meant it was born on a number year. Oh, it's effectively the same thing. Effectively. I just like know that like I probably don't know I'm probably not like 2 years off on my age. So guessing by even or odd usually gets me pretty close. Okay, so when we're writing this thing, I think we switch on the confidence now. If it's no, actually let's just only no or maybe. Just maybe we write nothing for now. Oh wait, maybe we can color this last digit accordingly, the blue value. That's not what I want. I don't know what I want to do here. Oh, Ginger, are you freaking out again? You should have shit when we went out earlier, man. Okay, this is easy. We write black on no. That's easy. Easy here. Maybe we do this for no and maybe. Let's just start there. And we need to define our lower thresh and higher thresh, so can we just do like, you know, lower 0.6? Anything over 0.6 counts or something? I don't know, man. Okay. Too high. Okay. Let's start with lower thresh at 0, higher thresh at 0.1. Let's just see if we can get like anything visualized. Okay, here we go. So it could be here that just like our thresholds are small. These are going to be like tunable later. Do higher thresh like plus minus 5% of the mean and lower thresh 35% of the mean. Yeah, that's a good idea, probably. I think for now I'm just going to tune these by hand, but I do agree. I think we'll just do this for now. And what did they say to do? It was like, if I am near a high confidence value, then promote the maybe. Right? I think that's what it said. So I think it's like, can we just do something like this? So let's just, I'm sure that there's like a better way to do this. Yeah, this is just a loop for var x iter is x sub 1 and y iter for while y it is less than y plus 1, less than or equal to, I guess. I don't really know what's happening, but we'll figure it out. Okay, I don't know, man. So we loop through everything around us. And if suppressed, yeah, this is like suppressed at yat times suppressed width plus x iterator. Confidence is equal to yes. Our confidence also becomes yes. Yep, and this is like technically this should we are, you know, leaking info. We're like progressing more than 1 pixel because like we're like modifying this thing as we're scanning it. But fuck it. Y to defined by x, true. So true right now. And then what is this thing pissed about? And then here we're supposed to be like something like this. I don't know, man. This is a disaster, but we do need to make sure that we don't go to bounds, so get fucked, I guess. Okay. So we should see, like, maybe a little bit of, like, increased lineage here. Yeah, we did. Some more lines came in now because we checked if things are close by. Okay, so I think that is a fully fledged canny edge detector. I think we have done the whole shebang now. All 5 steps, right? So we blur, find gradients, magnitude thresholding, set some hystereses, and you know, promote our maybes to yeses if things are close by. So what I'm a little interested in now, this feels pretty decent. I'm interested to run this on the barcode thing now that we've kind of done the whole thing. And if it looks good, then that would be kind of cool. So can we just do this? That image is fucking mega big. Do we have a scaled down version of it? Probably not, huh? Can we do new? I just want to like fucking Stacy's mom has got it going on. Okay. So let's crop this bad boy and then scale it down if we need to. Image. Crop. And then how big is this? This is like mega big. So we can scale it down to like pretty big, but not like mega big, you know? Like maybe 2048 across. Right, so this is still relatively good signal. And can we export as wherever the fuck we're working on this shit? Barcode scanner. Okay. Let's take a little peek. Okay, this is very promising, actually. Look at this. Look at this. I would love to overlay this stuff Plans to pull all this into Svimp. We should go back sometime. I would love to go back to Svimp. This is very promising. I think this is looking like very good, but I want to put it on top. So can we do like, I want to change the rendering here. Change the rendering to like, if yes, just like fucking magnitude 255. Who gives a fuck? Just to really make it stand out. Fuck. That's not what I was hoping for. I guess maybe our yes threshold is too low. Maybe I got confused with my lower and higher thresholds here. That the things that we were displaying were also being displayed as their threshold values, which are very low, right? So if we do like, you know, something way more reasonable. Okay, too high. We need to find a value that's not like crazy shit. Oh, maybe not. Maybe we were at the right threshold. It's just that... I'm surprised now. I'm surprised that we have so much speckle over here. Because I wasn't like, I don't feel like I was seeing that before, you know? Which is kind of interesting. So can we go back here, right? Like, can we try like kind of just strengthening it a little bit? Right, like here we're seeing very clearly like all of this stuff is dark and all this stuff is not. So there's something there for sure. Ginger, no. Okay, yeah, let's just try writing this on top of the image. So let's just take like the original. This is just image inner. I know. You need to give me like 5 minutes, dude. Because you didn't go last time, dude. Okay, so then we just use the original here. Original dot data at original dot width times y plus x. So now if we draw the line, we draw the line. Otherwise, we sample from the original. We do this. Fucking shadowing. Fucking shadowing. I guess all of this stuff is, there's a lot of yes in here. I guess is what we're learning. So maybe this has to go... like... if out is above, you know, like 50, then we do this. Else we draw the original. Right, there's probably something here. Yeah, look at that. Look at that. Tell me that that's not sick. So the thresholding here is wrong. But that's pretty fucking close. Pretty close, dude. Yeah, look at that. Look at that. So now, this should give us some really good signal. to do something better. Like really good. Really good. Yeah, pretty sick. Pretty sick. I would love to do more right now, but my dog is freaking out again. And I think she's having tummy troubles. So I think this is a natural spot to call it instead of going away and coming back. So tomorrow, I guess, we try to turn this into like strong blacks and whites and then use that to try to parse the proper barcode. But yeah, this is very solid. Very, very solid. I'm really happy with that. We might be able to kind of like discard some of the stuff that we did here as well, right? Like we have like some information that we can leverage for the barcode scanner, like for the fact that we know that it's all horizontal, the fact that we know they're going to be like strong edges, which is interesting. But yeah, I'll think about it. We'll come back tomorrow. We'll keep going. So cool. Thanks for watching, guys. If you like what you saw, we stream most days. We aim for 12:30 o'clock Pacific time to 4 o'clock Pacific time. It is 3:30 now, so anywhere between 3 hours ago and half an hour from now is when you should expect to see us live. Right now we're working on this meal tracker, so we're working on a barcode scanner. You know, we kind of get in the weeds here. But you know, there's lots of other stuff on the YouTube if you want to check that out. There's a YouTube link in the Twitch description. Some VODs go up there, but not all. Right, so for example, today, the segment where we were implementing the candy detector, that's going to go on YouTube, but the segment where we were kind of doing prep work and cleanup from the stuff from yesterday to make this stuff go faster, like the image kernel application stuff, that does not go up. The reason for that is because we need to keep the videos short and like targeted and YouTube algorithmically viable, so you know, good titles and thumbnails, whatever. But I still want to like put all the other stuff up, so we have a Twitch. The VODs on Twitch, YouTube, members, or on Patreon are available for the rest of the stuff. We put them behind the paywall so that we have something to give people who want to support the stream. The stream will stop happening when I run out of money and need to get a job. So if you want to, you know, increase the lifetime of the stream, consider using your Twitch Primes, subbing on whatever platform makes sense, whatever. But obviously, no pressure. I think that's all the plugging we got to do. YouTube, peace out. Twitch, let's find someone to raid. Ginger, let's go outside.